Hey all, welcome back to the lab. In this video, we're going to be talking about, or really trying to answer, the question of will removing Python's GIL make it significantly faster? So I recently came across a discussion about Python's 7-year plan to remove its GIL, its global interpreter lock, and the impact it would have on the language. The GIL has long been cited as a blocker for performance improvement in Python, so if it could make Python significantly faster, it could change how we view the language and what tasks it's suited for. Generally, we consider, like Rust and Golang and C#, Java on the faster end of languages, and then the more interpreted things like Ruby, Python, even JavaScript are really towards the lower end of things on the perf scale, which does lead to some, decision making about what this language is actually good for. Now, I personally like to keep tabs on programming language performance as I use it as a factor for choosing between languages for my different projects. Now, I mostly do backend, so performance is not the most important thing. I'm doing like web services, a lot of waiting on I/O, so it's often not the most important thing for my workloads, but it's still something I like to consider, especially as I like simple scalable systems, so the more that my system can do as a single or simply vertically or small horizontally scaled system, the less work I have to do myself as a solo dev. So in this post, we're going to explore that question: will removing Python's GIL make it significantly faster? All right, so what is Python's GIL? So the GIL, or the Global Interpreter Lock, was created to solve thread safety and memory management. Python uses reference counting for memory management, which is basically how it's determining when memory can be garbage collected. If there's still references, then it's probably still being used somewhere. If there's no references, then it's like, nobody's using this anyway. Let's schedule it for deletion. And it went with a single global lock, the Global Interpreter Lock, to ensure that no race conditions exist when updating reference counts. Because if you do have race conditions when you're updating reference counts, that could lead to corrupt memory because maybe you have too many reference counts, so this thing is like never deleted, or you accidentally decrement when there's still a reference, and so now the memory has already been deleted but you're still trying to use it, and so this is what it's trying to prevent. And this is relatively simple and relatively fast and single-threaded programs, and so for many cases this works quite well. For a lot of general purpose programming, this really it just is not a big deal at all, as we'll see. Now onto the problem with this. So Python's GIL prevents true parallelism. The problem is that Python's GIL prevents true parallelism. Most variable reads and updates involve the GIL, both shared and local variables, as they may incur reference count changes, which means Python code is constantly interacting with the GIL. This means that even when you spin up multiple threads in quote-unquote parallel, those threads will constantly be using variables and thus waiting on the GIL for their turn to process. And what this means in practice is that most threads in Python don't actually run in parallel, but more sequentially, which removes most of the benefit because they're going to be trying to run in parallel, but every time they're accessing a variable, basically, they're going to wait on the GIL, lock so that they can actually update the reference counts and stuff. So they're trying to run in parallel, but they keep waiting on the same thing, which basically means that it's running sequentially. Now, to get around this, you can spin up multiple processes instead, as each process has its own GIL. The drawbacks with this approach is it's harder to work with, and processes don't typically share memory, which can be a problem for data-intensive apps like machine learning, scientific computing, and data processing, which is kind of where Python's ecosystem is king. And it's a bit harder to work with and clunkier because I don't think it's as easy to pass messages back and forth. I think it also has some overhead in terms of like the runtime and stuff. But this is, I believe, how many apps have done parallelism in the past. Like Django, I believe, runs with multiple processes. So it basically is parallel, even though it's not using threads. But it does have some drawbacks. So just like as an example, working with a 1 gigabyte data set in memory, if you're doing some like data processing or something, if you multi-process to 4 processes, it now takes up 4 gigabytes of memory because it can't share that memory very easily across processes, which can be cost prohibitive depending on what you're working on, especially with like AI workloads or if you're training them, where I think they often the memory itself is one of the bottlenecks. This could be a problem. But I want to caution that the GIL problem doesn't affect all types of programs, as the GIL does get released in many cases. And so for I/O operations like file reads or network requests, the GIL usually gets released. For C extensions that explicitly release it, like NumPy does this, and often this is honestly how Python has gotten good at its data processing in general, is because it does offload a lot of the heavy lifting to C, so you get your nice Python wrapper, but then you get the performance of C in a lot of the critical areas. And then for sleep and blocking calls, like waiting on an event to come in or a queue, this often releases the GIL as well. So a lot of things can be waiting at once without, blocking any other thread that's actually doing stuff. And so while the GIL can be a major problem for larger parallel workloads, for many other workloads like a web server, it's actually not a big deal. And so it just doesn't matter that much to them. I was also curious about how this works with async await. I think async await is really a great paradigm in a lot of different languages, but it is very confusing to people, and it is implemented in different ways in different systems. So I was curious how this impacted the GIL or interacted with it. And it turns out that, in Python, async await runs with concurrency and not parallelism. And so this can help a single thread do more stuff even when the GIL is in play. And the way it works is basically when you say await something, it's going to be like, hey, this thread is blocked on this if it's not, returning immediately. And so that thread is going to go away and work on something else that's been blocked by async await. And so that the thread is constantly doing work. And so your total throughput of work can increase over time, but maybe that single piece of work itself might not go as fast. And because it is the single thread, it's not really impacted by the GIL because it's just one thread going the whole time. There's no other threads it has contention with the GIL. And so GIL removal won't really impact async await because it's still working on single threads. But if you want to do multi-threading across async awaits, then that's when you could actually get benefits from this. So the question we came here to solve is, will removing the GIL make Python significantly faster? And so Python is about 2 years into its 7-year roadmap to remove the GIL, so we can look at some early results to get an answer. And the early results say yes, but it is workload dependent. So where it's faster today is with well-designed parallel workloads. And so here we see that COD speed was able to achieve 2 to 4x speedups in PageRank algorithm using no GIL instead of GIL. And so we see that for single threads, and I guess the way to read this is on the left is the amount of seconds that it completed in, so how fast it is, so lower is better because it was faster. And then here it's grouped by the type of workload, and then the colors mean the different versions of Python, and when it's at 3.13, whether they use the GIL or the no-GIL. And so here for single threaded processing, we actually see that 3.13 GIL and no GIL ran slower. There's actually overhead, as we'll talk about in a minute. For threads, the GIL is actually even more slower than 3.12 and 3.13, but no GIL is significantly faster. I believe this ran in about 0.4 seconds, and this is about 2, so 75% faster. And then for processes, 3.13, both GIL and no GIL, is a lot slower than the earlier versions of Python by about 2x. And so yes, we're seeing significant speedups on this threaded version when we have no GIL, but for other areas where it's not specifically optimized for those, it's actually slower and sometimes much slower. And for another example, Backblaze did a benchmark on file I/O, and I think they were just writing a ton of files all at the same time, and they've run it across several different versions of Python, so each version of Python gets a little bit faster, and then when they tried no GIL, they got much larger improvements, which is about, looks like around 8x improvements by using no GIL for parallel file I/O. For more info on these benchmarks, because, again, all benchmarks have asterisks, you can check out the links here. One thing to note is that many libraries are not yet compatible with no GIL, and thus may require significant rewrites for users to benefit from these new features. And so, there's some caveats here of it's going to take some time for a large part of the ecosystem to even benefit from this stuff, and it's going to be kind of one of those things that Rust faced with asyncs, and that there's multiple, or for at least some amount of time, there's going to have to be multiple versions of packages to make them compatible with the different versions of Python that people are using. And so it's going to be a little bit messy, and it's going to take some specialized time and thought to make this even work for you. But this is the direction that Python seems to be going. And so now where it's slower. And so there's basically a 20% memory overhead for the additional locks that no-GIL requires, because they're kind of moving from that single lock to multiple locks around a lot of the data structures and stuff, and I guess variable reference counts. I don't know exactly how it's implemented, but this is a lot of extra work that they're trying to do, or Python's trying to do under the hood, and so it does incur extra memory. And then this actually did incur a lot of performance hits as well. So the single-threaded performance in Python 3.13 is actually 40% slower than it was in previous Python versions. And they're working on this, 3.14 is only 10% slower. But this is to say that, this no-GIL parallelism required a lot of internal changes, and this didn't come for free and actually incurred pretty significant decreases in performance for a lot of general Python workloads. And so, the takeaway here is that GIL removal did unlock true multi-threading in Python, but it came with some baggage and likely won't speed up most general workloads without a lot of special attention. And this might just be like, researching if the package that you want to use even has this, but if it's not no-go compatible, that might actually mean rewriting it yourself to make it compatible. Next. So Python is not a fast language. Removing the GIL improves its performance in multi-threading, but so far does not appear like it's going to make a meaningful performance difference for most Python workloads. So if you're looking for a performant language, Python probably isn't it, but it is still plenty fast enough for most use cases, and most people choose it for how easy it is to read and write anyway, not really its performance characteristics. So it's still a solid choice if that matters to you. I personally rank Python as a B-tier language, so, pretty good, and have no qualms with people who choose it. Now, if you like this post, you might also like how to run a simple Python program in a Docker container. You might also be interested in build a simple result type in Python and why you should use them. And finally, 5 reasons F# is a great Python alternative for scripting, side projects, and enterprise applications. So that's it for this video. Thanks for watching, and I'll see you in the next one.